Good morning, all. Today we are starting our next lecture on hydraulic machines, and today we are starting our 15th lecture. Till now, we have completed our 14 lectures on hydraulic machine, and in 14 lectures, we discussed the first module. Okay, in the first module, we discussed the impact of jet, the force exerted by the jet of water on the plates, on various types of plates, and the propulsion of ship, and force exerted by series of vanes, etc. Okay. And today we are starting our next module, that is the second module. In second module, we are mainly dealing with the hydraulic machines. We are getting into the hydraulic machines in depth. And first of all, we are discussing the hydraulic turbines, and in which we are discussing the Pelton wheel turbine. Okay. So as we are talking about this module number two, it is mainly a problematic. Most of the problem or sections arrived here is numerical ones. Okay. And first of all, we will do some derivations, the basics derivations, and we'll understand how the hydraulic machine is working, and then the various components of these hydraulic machines, especially the pellet and turbine. Okay. After that, we will get into the next section. That's the numerical section. That is where we will do the problems based on the velocity triangles. As we already know that we are already studied the velocity triangles in the first module. So it's simple in case of the second module. Well, it's just simply the continuation of the velocity triangle first module itself. And almost all the terms, that is velocity of whirl, velocity of flow, gate weight angle, vane angle tablet, vane angle insert. All those terms are same. Only the arrangement of the directions, this is the only change. Okay. So let's have a look at the second module. So first of all, hydraulic machine. So my question is, what do you mean by this hydraulic machine? In our previous lesson, we studied our basics of the engineering, everything was studied. What do you mean by machine? So machine means normally it's a device which is used to convert one form of energy to another form. So machine is any device which convert one form of energy to another form. Okay. So if we convert given it from input energy form, and it will be converted to the an output energy form. Okay. So this hydraulic machines means it is used to convert the hydraulic energy from one form to another to a form. Okay. This is the hydraulic machines. So hydraulic machines means that device which is used to convert hydraulic energy. So hydraulic energy may be converted to mechanical energy, or hydraulic energy can be converted to mechanical to hydraulic to mechanical, or mechanical to hydraulic energy. As we know that in the fluid mechanism, we stated that the hydraulic energy means the total energy processed by the fluid. So what are the various types of the energy that a fluid can occupy? For example, in dam we know that the water is stored in the reservoir, and from height we are trying this vehicle or carrying this water to the strike this power generations, that is the turbines. So the position of the water is, that is the position energy processed by a fluid by which of its position, that is the potential energy. When the water is flowing, it's the energy of the fluid by virtue of its motion, that is the kinetic energy. And another one is the pressure energy. Okay, so there are various forms of energies are processed by this fluid. So we are utilizing this energy. Okay, so hydraulic energy means the kinetic energy, potential energy, and pressure energy. So this kinetic energy is converted to the mechanical energy. Mechanical energy means it's a shaft work output. So this hydraulic energy can be used to rotate the shaft. Okay, and work output is produced. And while the water will be strikes on this shaft or plate, we know that a force is generated, work output is produced. And in the case of a series of veins, we studied that when this particular place, when a series of veins are attached over a circumference of a rotor, we can produce a work output. Okay, that is rho a into v minus u into v minus u. So various terms we studied. So based on the energy conversion, we can classify the hydraulic machine. So hydraulic machines which is either converting the hydraulic energy to the mechanical energy, or mechanical energy to the hydraulic energy. Mechanical energy means the shaft work output, and hydraulic energy. Okay. And based on the conversion, we can classify the hydraulic machines into two mainly. Okay. They are hydraulic turbines and hydraulic pump. The machines that convert hydraulic energy into mechanical energy are known as turbines, and those which convert the mechanical energy into hydraulic energy are known as pumps. So in this module, we are discussing the hydraulic turbines. So here I am showing the schematic representation of an hydroelectric power generation system. Here you can see. Okay, both are same, but just have a look. Here you can see a dam here. What is the purpose of the dam? Is used to store this water, and here it is a reservoir of the water, and here the water is stored. So it's kept at a certain height. Okay, so this will be processed by some energy, that is the potential energy. Okay, and here you can see a pipe which is connected to the dam and to the turbine. Okay, these pipes of very long diameter, and lengthy pipes or metallic pipes, sometimes maybe concrete. Okay, concrete masonry structure. Okay, and these pipes are known as the penstock pipes. These are used to carry water from the reservoir of the dam to the turbine inlet. And here you can see that the turbine is coupled to a generator. The purpose of generator is to generate electricity. Okay, here we are showing the schematic representation of the hydroelectric power system. This is the general layout. Then here you can see a dam which is constructed across the river to store the water. A dam is constructed across the river for storing the water. And the pipes of large diameter called penstock pipes, which carry water under pressure from the storage reservoir to the turbine. And next is the turbine. This is a high turbine with a number of vanes fitted on it. And next is the tail race. This is a tail race region. Okay, tail race is the channel which carries water away from the turbine. So here the water is coming from the reservoir, and this water is flowing over the penstock pipe and strikes the turbine, and work is done on the turbine. After that, this water is carried away from this location by this channel, and this channel is known as the tail race. It's a channel which carries water away from the turbine after water has been worked on the turbine. The surface of water in the tail race channel is also known as tail race. Okay, and this one equal to the head race. This is tail race. Here it is the tail race, and here it is the head race. Now we are studying the various heads in the turbine system. For that, one more thing. So here the turbine is rotated by means of this water that is coming from this reservoir, and work output is produced. And this turbine shaft is connected to a generator. Okay, here you can see this turbine is coupled to a generator. So its purpose is to generate electricity. When the turbine shaft rotates, and since it is connected or it is coupled to the generator will be worked and the electricity is produced. Okay, and is transferred to the grid. This is what taking place in the hydroelectric power system. Now let's look at the various types of the heads. Okay, here you can see this is the head race and this is the tail race. So the gross head, that is denoted by H subscript G. Gross head is the distance between the head race and the tail race. The difference between head race level and tail race level when no water is flowing is known as gross head. And second one is net head. Net head is denoted by the letter H. Net head is the we can also call it as an effective head, and it is defined as the head available at the inlet of the turbine. Net head is the head available at the inlet of the turbine. Okay, because then this is the gross head is the difference between the head race and tail race. But actually, we won't get this total head. No, means this gross head because there may be some losses due to friction between the water and the penstock. Okay, as the water is flowing through this from the reservoir, the water is flowing through this penstock pipe, and after that it strikes the turbine. So in between there is a chance of the friction may be there. So due to this friction, there may be losses of the energy, and also there will be bends will be there like this. Okay, there is a bench, and there's maybe pipe connections will be there, and due to these factors, loss at the entrance of the penstock and also the loss at the exit of the pipes. I think you studied the pipe losses in your fluid mechanics lessons. So the losses due to the sudden enlargement, sudden contraction, pipe fitting, bench, etc. So here in this case of penstock pipe, the pipe losses occur due to the loss at the entrance of the penstock and the exit of the penstock, and due to the bends and due to the pipe connections. Head losses will be occur, and this head loss is denoted by HF. HF means head loss due to friction. Okay, so we already studied the HF equation for the HF, that is head loss for friction, that is equal to 4F LV square by 2GD. Darcy-Weisbach equation. HF is equal to 4 LV square by 2GD. That is a Darcy-Weisbach equation. So I think it's not time. In this time, I'm not ready to just recapitulate all these things that we have studied in your fluid mechanics. I think hope you all remember those things. Okay, if anybody have any doubts, please go through your fluid mechanics lessons. So HF is a Darcy-Weisbach equation. That's equal to 4 of LV square by 2GD, where F is the coefficient of friction, and V is the velocity of flow in penstock, and L is the length of penstock. This is the diameter of penstock. So I think hope you all clear that. This is the gross head, this is the net head, and this is the HF. So the net head will be equal to gross head minus HF. That is net head plus HF is equal to gross head. So this section is the loss that is occurring in the head, and the water is coming through this way, and at the end of the penstock pipe you can see a nozzle is attached. Nozzle means is a tapering cross section. So let assume that that is the A1 B1 is equal to A2 B2. That is the continuity equation. So here you can see that area is more, and here you can see that area is less. It is a tapering section. Okay. As the area decreasing, so by continuity equation that discharge is constant. So area decrease means velocity is increased. So water at high velocities allowed to strike on the vanes. So this is the rotor. This is the central shaft of the turbine, and this is the turbine rotor. Okay, other rotating element, and the outer periphery of this is the circumference, and the outer periphery of this rotor you can see the number of vanes. Okay, a bucket shape, a double hemispherical shape buckets or vanes are attached. The water is coming and strikes these buckets, and this force is exerted, as you stated in the case of force exerted by jet of water on series of vanes, and this rotor will be rotated and the shaft work output is produced. This is what happened in the case of turbines. So now let's look at the various type of efficiencies of the turbine. Generally there are four types of efficiencies. They are first one is hydraulic efficiency, second one is mechanical efficiency, third one is volumetric, and fourth one is overall efficiency. Okay, so now let's discuss each type of efficiency in detail. Let's understand what you mean by these efficiencies. Okay, first of all, the hydraulic efficiency. Hydraulic efficiency means is the ratio of power delivered to the runner to the power supplied at the inlet. Okay, power delivered to the runner. So runner means the rotating element of the turbine. So how much power is delivered by this moving water to the runner and to the power supplied at the inlet. So how much energy supplied at inlet is available at the runner? This is our question. Normally the power at the inlet of the turbine is more. Okay. And this power is goes on decreasing as the water flows over the vanes of the turbine due to hydraulic losses at the vanes, and the veins may not be smooth. In previous sections, we discussed that the assumption and during derivation that the veins are assumed to be smooth. Okay, but in actual practice, the veins are not smooth. So at the inlet, we will get the maximum power, that is the power supplied at the inlet, and at the runner, the power will be get decreased due to the various reasons of the friction and the losses of various losses are there. Okay, the power is goes on decreasing as the water flows over the veins. The jet of water strikes the veins and after traveling through the veins is coming out. Okay, so in this traveling, during this traveling, there will be losses will be occur. So mathematically we can say that hydraulic efficiency is equal to rp by wp, where rp is the runner power, that is the power available to the runner of the turbine, to the wp, that is the power supplied at the inlet. So water power is equal to rho qgh by 1000 at that much kilowatt. Okay, so we will discuss these equations in the problem sections. And next efficiency is mechanical efficiencies. Mechanical efficiency is defined as the ratio of the shaft power to the runner power. So the power delivered by the water to the runner of the turbine is transmitted to the shaft of the turbine. Okay. So the power from the vanes, the power is the vanes are force exerted in the vanes, and this rotor is rotating. Okay, and this rotation is transferred to the shaft of the turbine. Okay, so due to some mechanical reasons, the power available in the shaft of the turbine is less than that of the power delivered to the runner. So the ratio of power available at the shaft of the turbine, known as SP or PP, that's brake power, to the power delivered to the runner is defined as a mechanical efficiency. Mathematically, we can write as SP divided by RP, that is shaft power to the runner power. And next one is the volumetric efficiency. Is mainly deal with the volume of the water strikes. That is the ratio of volume of water actually striking the runner to the volume of water supplied to the turbine. The volume of water striking the runner of the turbine is less than that of volume of water supplied to the turbine. Some of the volume of the water is discharged to the tail race without striking the runner of the turbine. Thus, the ratio of volume of water actually striking to the runner to the volume of water supplied to the turbine is defined as volumetric efficiency. For example, if you assume that a particular unit, okay, X unit of water is supplied totally, but unfortunately there's some losses in the form of some water not even directly strike this runner, okay, or this base. Instead of striking, they are directly released to the tail race. For example, a Y unit of water is released out. So the at the inlet or the water actually striking the runner will be equal to X minus Y units. But we supplied the X units, and X is always greater than this Y. Okay, so there will be losses. So this is known as volumetric efficiency. And last one is the overall efficiency. It is defined as the ratio of power available at the shaft of the turbine to the power supplied to the water inlet of the turbine, that is output by input. So the output of the turbine is the shaft power and input is the water power. Power supplied by water at the inlet. And shaft means the power output of the shaft. Okay. So we can shaft power by water power. And this shaft power by water power can equal to the shaft. We can, for example, this shaft power by water power. If we multiply the both sides, that the numerator and the denominator, by the runner power, what will happen? And rearranging, we can say that a shaft power by water power multiplied by runner power by or we can say that SP into RP divided by WP into RP. On solving and rearranging, we will get that is equal to mechanical efficiency into hydraulic efficiency. That is overall efficiency is equal to mechanical efficiency into hydraulic efficiency. Please note it. Okay. So all these terms you study these things and I explain these things now, and you can just put it in on equations and you can understand that things. Okay. So just go through this as an assignment. Okay. So overall efficiency is equal to mechanical efficiency into hydraulic efficiency. Next we are studying the various classifications of the hydraulic turbines. Let's go through each of them. Okay. First one, the hydraulic turbines are classified based on the energy that is available at the inlet, according to the type of energy available at the inlet. There are two classifications, that is impulse turbine and the reaction turbine. Okay. If the energy available at the inlet of the turbine is only kinetic energy, then it is known as the impulse turbine. The kinetic energy plus the pressure energy is available at the inlet of the turbine, then it is known as the reaction turbines. Okay, we are mainly dealing with the impulse turbines and the reaction turbines. And in this module, we are dealing with the impulse turbine in detail. So energy input and energy available in inlet of the turbine is kinetic energy only in the case of impulse turbines. Okay, we are not getting into deep in these things. We are just according to your syllabus, the bases are good. So we are just seeing these basic things only. Okay. So, based on the energy input means based on the energy, there is only kinetic energy available in the case of the impulse turbine, and the kinetic energy and pressure energy is available in the case of reaction turbines. Okay. Next one is the according to the direction of flow through the runners. That classification based on the tangential flow. The tangents, the jet of water strikes this tangent. The flow is tangential. Okay. And radial flow along the radial direction the flow is taking place, and this area, the next one is the axial flow, and this the flow is taking place along the axis of the rotation, and then was this mixed flow. Okay, is a combination. And next one is according to the head and the quantity of water, how much quantity and how much water about the head. Okay, h that is available. Okay, and first one is the high head turbine. High head means those turbines which is working at high head. The high head means that is about greater than 250 meter. Okay, higher the head means the quantity will be less. Okay, high head means high head, but there's less quantity. It is a high head turbine. That is a Pelton wheel turbine. And second one is a medium head turbine. This medium head turbine is working under the medium head. Medium head means is normally ranges between 60 meter to 250 meter, but they require relatively large quantity of water as compared that of high head turbines. And next one is the low head turbines. And these turbines working at a head which is less than 60 meters, and they requires very less quantity of water. Sorry, not very less quantity, very large quantity of water is required. Okay, so please cut it here. Like a very large quantity of water because the head is low, so means the quantity is high. High head means head is high, quantity of water is required is less. Okay, low head means head is low and the quantity of water is very high. Normally, Kaplan turbine is an example for the low head turbine. And next one is the according to the classification is based on according to the head available. No, sorry, not head available. According to the position of the shaft. According to the position of shaft, we can classify them into horizontal turbines, and next one is the vertical turbines. So in the case of horizontal turbines, the turbine have a horizontal shaft, and that's in the case of the parent wheel. In vertical turbine, the turbine has vertical shaft. That is the Francis and Kaplan turbines are the examples. Okay. So first of all, let's discuss the working of a Pelton wheel turbine. This is the various commands of this Pelton wheel turbine. Here you can see this is the penstock pipe that carries the water from the reservoir to the turbine inlet.